One-to-one functions are nice. There is a direct mapping, a consistent correspondence. X going to Y means Y goes to X. And because of that, because you can go either way, it's not where you can only be certain going X to Y. You can go Y to X. So it's not really like independent dependent. And because of that, one-to-one functions have inverses. What is an inverse? An inverse is a function that undoes what the other function does. Let's say you plug in a number into the function and you get an output. You plug in A, you get B. Well, then its inverse would take in B and output A. Where the function takes X and outputs Y, its inverse takes Y and outputs X, because there's that one-to-one correspondence. So you can always backtrack to where you came from. Another way to say that is if f of A equals B, then f inverse of B equals A. Let me give you an example of an inverse. Here's a function, f of x equals 2x plus 1. If I draw a little chart of that, a table, I should say, if you plug in 0, you'll get 1. If you plug in 2, you'll get 5. If you plug in -1, you'll get -1. So f inverse would take in these outputs here and it would give you back those inputs. So f inverse of x should have a table that looks like this, where all those y's become the inputs here and all those x's would be the outputs. Now if you actually took time, you would find that this is a linear function here. This one's linear over here and this one's also linear. And it actually turns out that this function has a slope of a half and a y-intercept of a half, but can also be written like this. So that is actually the inverse of this function. I'm going to explain how to get this without going through and trying to figure out, oh, there's a slope here because this one's going, let's see, up 2 over 4. This one's going down 3, down 6. And you can see -3 over -6. It's the same as 2 over 4 is equal to 1/2. So we could find the slope, we could find the y-intercept, and we could get this function. But is there an easier way? And the answer is yes, there is. But before I go there, let me show you how to get the inverses of some other things. So, for example, if you're given a function in the form of ordered pairs, and you're asked to find the inverse. So the function is a discrete set of ordered pairs. Let's say g is the inverse of f, then g would look like this. It would be the ordered pairs swapping the inputs and the outputs. So there you go. Now, over here, if I ask you to find the inverse of h, let's call it h inverse, you actually run into a problem. Because when you go like this, you get 0, 1. When you flip these outputs, you get input outputs, you get 3, 2. And over here, you get 0, 4. But let's think back. A function cannot have the same x going to a different y. So why did this happen? Why is this inverse coming out to be not a function? And the answer is, if you look back up here, the original function, h, was not one-to-one. We had one y that had two x's. And because of that, here was our mapping of h originally. 1 went to 0, 4 went to 0, and 2 went to 3. So we had those points. Well, if we swap the x's and the y's, then we're going to have something that looks like this, with 3 going to 2. And now, because it did not pass the horizontal line test here, it cannot pass the vertical line test when we swap the ordered pairs. Because think about it, if we're swapping the x and the y, it's like we're swapping the x-axis and the y-axis. So it's like we're rotating or folding this thing up across this line. We're like reflecting it over, okay? And if we do that, what didn't pass the horizontal line test before will not pass the vertical line test after. Let me give you another example. What if I give you a graph and you're asked to find the inverse? Well, firstly, we already saw that that graph had better be 1-to-1. So up here, no inverse because H not 1-to-1. So if I'm giving you a graph, it better be of something that is 1-to-1. So let me say I give you this. That's -1, 0. We'll say this is 0, 2, and so this will be my function f. First of all, is it 1-to-1? Well, every horizontal line only crosses it in one place, so it's 1-to-1. And then let me put down my ordered pairs. So I had -1, 0. I had 0, 2. And this point was 5, 4. So to draw its inverse, I would have to connect with a similar smooth curve the reversal of these points. So -1, 0 becomes 0, -1, which is right here. 0, 2 becomes 2, 0, which is right here. And 5, 4 becomes 4, 5, which is up here. So the inverse of f would be a curve kind of like this, where the points would be reversed, 4, 5. And you'll notice that it's like I folded the x-axis up to the y and the y down to the x. So when you look at a function and its inverse, they will always have symmetry about the line y equals x. By the way, because y equals x, it's its own inverse, and we'll talk about that later. Before I show the method of finding an inverse from a function's equation, we need to define formally what an inverse is. So here's the definition. Let f be a 1-to-1 function. We have to start with a 1-to-1 function. Then g is the inverse of f, and vice versa. F is the inverse of g if and only if the following two conditions hold. So there are two conditions for us having a inverse. The first one is the composition of f of g of x has to equal x for all x belonging to g. And the other one is g of f of x has to equal x for all x belonging to f. Well, what does that mean? That means if I take in x, the first condition means I take x, I plug it into g, and I get g of x. Well, when I take g of x and plug that result into f, it should give me back x. Remember what I said earlier. If f of a equals b, then f inverse of b should give you back a. So let's think about, we're doing a composition now. If I plug in a into f, I get b, and what's f inverse of b? It's a, if they're inverses. So whenever I plug in x into this composition, I should get back x, or in this composition. But both must be true. It can't just be true for the one composition and not the other, because then it's not a true inverse. Let me give you an analogy. If f and g are inverses of each other, the following should be true. So this one here, the first condition we said was x goes into a machine which messes with it, and that machine is called g. And when it comes out, it's no longer x, it's g of x. It has been transformed by g in some manner. Well, that result, that output, we're saying in here, in this composition, is going to go into f. So here's f. F is going to do some stuff to it. And out will come f of g of x, because g of x went in, f messed with it, so out comes f of g of x. Well, what they're saying here is that f of g of x if f and g are inverses, then it better be the case that this is actually equal to x. So whatever this is, it better equal x, and vice versa. So I have x. What does it go into? X goes into f first. Here's f. Goes in, out comes f of x. Where's that going? It's going into another machine called g, and out comes g of f of x. And those things, that composition better be x every time. So the question is, how do we prove it? How do we prove that two things are inverses? We know how to prove one-to-one. We show that f of a equals f of b implies that a equals b. Well, how do we do proving two functions are inverses? Well, actually, you have to show that both conditions hold. That f of g of x gives you x and g of f of x. So for this one, I said earlier that these two were inverses of each other, but I didn't tell you how I got that. So here we're going to prove that they are. So I want to find f of g of x. Well, that means g of x, this function, is going into f. So I'm going to take 2x plus 1, and I'm going to replace x with g of x. So this function, which is g of x, is going in for the input of f. And you can see these suckers cancel. We get x minus 1 plus 1, which is x. Good, good. That's awesome. But it's not enough. I have to prove both conditions hold. So I keep going and I check, does x minus 1 over 2, if I plug in 2x plus 1 into that, so 2x plus 1 goes into x minus 1 over 2, does that give me x? And the 1's cancel, 2 over 2 is 1, so I get 1x, which is x, and yes. So that shows that they are inverses of each other. Let's show that f of x equals x squared and g of x equals the square root of x aren't inverses. So let's suppose that I didn't know that, and I was trying to prove that they are. So let's just do the composition here and see what happens. If they are inverses of each other, then the result should come out to x. Alright, so I'm plugging g of x into x squared. G of x is the square root of x. I'm plugging that into x squared. So when I square the square root, I get back x every time. And since the square root can never come out negative, I don't have to worry that my square is getting rid of a negative for me. So that's nice. It came out right. Let's check g of f of x. Alright, so this time I'm plugging x squared into the square root. Now here's the problem with x squared. I know that if I square a number, it gets rid of the negative. So actually what I get back here is the absolute value of x. Let me demonstrate that better. If I take g of f of 2 and I plug that in, I get 2 squared, which is 4 square rooted is 2. So it looks like they're inverses. But let's not forget that we also have negative numbers in play. And if I plug in a negative and square that, that negative disappears. And I can never get a negative out of the square root. So there you go. They are not inverses of one another because I do not get back what I started with. Another way you can think of that is f of x is x squared, which is not a one-to-one function. So it can't possibly have an inverse. If it did have an inverse, that thing would not be a function because it does not pass the horizontal line test. And so these 2 points that are aligned horizontally here would be aligned vertically if it had an inverse. Let's look at g of x. G of x is a square root function that has an inverse, but it's not x squared. It's x squared under the restriction that the inputs are strictly positive. So if I graph this, it looks like that. So its inverse would actually have to look like that, which is half of a parabola.